Semigroups and their representations, Lecture 18, Representations of Inverse Semigroups. Let us start with a quick recap of how we construct simple modules over finite semigroups. So let S be a finite monoid and K a field. Let J be a regular two-sided class in S. Let E be an idempotent in J. Let LE be the left class of S containing E, and let HE be the H class of S containing E. Since E is an idempotent, this class is a group, which we denote by G. Now the linearization of our left class LE becomes a bimodule, where the semigroup S acts on the left and our group G acts on the right. Furthermore, sending a simple G module V over our field K to the top of the module obtained by inducing V all the way up to S using our bimodule, so we use a tensor induction. We take K of LE and tensor over K of G with V. This is an S module, and this module has a simple top, so we take this top. So the map which maps V to the simple top of this module is a bijection between the set of isomorphism classes of simple G modules over K and the set of isomorphism classes of simple S modules over K with apex J. Now let us describe our inverse setup for today. Let S be a finite inverse monoid and K a field. Then S is of course a regular monoid. In particular, each two-sided class of S is regular. So let J1, J2, and so on Jk be a complete and irredundant list of two-sided classes in S. For each I between 1 and k, choose and fix some idempotent EI in the class Ji. Let Li be the left class containing EI, and let Hi be the H class containing EI. Then this Hi is a maximal subgroup, and we denote it by Gi. Let Fi denote the functor of tensoring over K of Gi with the linearization of Li. That's a functor. The input of this functor is a Gi module, and the output is an S module. So now we can formulate the main result for today's lecture, and that's the following theorem. For a finite inverse monoid S, with the above notation, we have that for any I between 1 and k, and any simple Gi module V, the S module Fi of V is simple. In other words, if we start with V and tensor it over K of Gi with K of Li, this module not only has simple top, and that's what we proved on the previous lecture, but under the assumptions that we work with an inverse semigroup, this module is simple on the nose. Therefore, for inverse semigroup, the correspondence which sends V to the top of this induced module can be simplified in the following way. V is sent directly to this module Fi of V, to the module K of Li, tensor over K of Gi with V. So we will prove this theorem on the next slides. So let us prove our theorem. Let H1, H2, and so on Hm be a complete list of H classes in Li. We assume that Ei belongs to H1, and note that none of the other Hj's contain any idempotence. This is because we know that each left and each right class of an inverse semigroup contains a unique idempotent. For J between 1 and m, let Fj be the unique idempotent in the right class Rj, which contains Hj. Then F1 is equal to Ei. Let Kj be the maximal subgroup which corresponds to this Fj, and then of course each Kj is isomorphic to Hi. So all maximal subgroups within the same two-sided class are isomorphic. We claim that if J1 is different from J2, then the product Fj1 times Fj2 cannot belong to Ji. Indeed, if it would belong to Ji, it must be in the left class of Fj2 because that's on the right, and hence it should coincide with Fj2 because Fj2 is the only idempotent in its left class. At the same time, the idempotents of inverse semigroup, they commute, and so we can do the same argument for Fj1 and get the same outcome for Fj1. And so we get a contradiction that Fj1 equals to Fj2. Consequence of this is that the product of Fj1 and Fj2 doesn't belong to J, and so it annihilates Fi of v, because J is the apex of Fi of v, and this product is necessarily smaller than J. At the same time, Fj acts as the identity, if we multiply it on the left, on the whole right class Rj, and in particular on Hj, because it's a subset of Rj. Now consider the element of the module Fi of v, which looks as follows. We just take an element in the general form. Sum over all j between 1 to m, then sum over all h in hj, and then we take h tensor some element vh in v. By the above, if we multiply fj with a summand h tensor vh, we get the summand back if h belongs to hj, and we get 0 if h doesn't belong to hj. So multiplying with different fj's, we can get all individual elements of the form sum over all h and hj, h times vh. Next, we know that each aj is free of rank 1 as a module over gi. Therefore, as a kj module, the module when we tensor k of hj over k of gi with v is just a copy of the module v, but now considered as a module for our group kj instead of gi. And these are two isomorphic groups under our identification. Therefore, from any non-zero general element of the form sum over h tensor vh, by left multiplication with elements of kj, we can get all other non-zero elements of this kj module. Also, for any pair of different j and j prime, by Green's lemma, there is an element S in our semigroup such that the map sending x to Sx is a bijective map from Hj to Hj prime. Therefore, applying S to our sum, we get a similar sum with an element S on the left, but now in the original sum h belongs to hj, and in the new sum sh belongs to hj prime. So starting from a non-zero element, which corresponds to hj, we can multiply on the left and get a non-zero element which now corresponds to hj prime. And this simply implies that starting from any non-zero element of our module Fi of v, we can, using the above manipulations, get all non-zero elements of this module, and so this module is simple. As a corollary, we can give an explicit formula for the dimensions of simple modules for inverse monoids. So corollary, in the setup of the previous theorem, the dimension of the simple module Fi of v equals the dimension of v times the number of right cells inside the two-sided cell ji. We know that this is equal to the number of left cells inside this two-sided cell, because for inverse semigroup, each J cell contains the same number of left and right cells. Proof. Fi of v, by definition, is k of Li tensor over k of gi times v. As a vector space, this tensor product is a direct sum of different k of hj's tensor over k of gi of v, and each k of hj is free of rank 1 over k of gi, so the dimension of this smaller tensor product is exactly the dimension of v. And the number of summons here is equal to the number of right cells inside Ji, and this implies our corollary. Finally, we can also describe in which case the semigroup algebra of an inverse semigroup is semi-simple. So corollary, let S be a finite inverse monoid and K an algebraically closed field whose characteristic does not divide the cardinality of any maximal subgroup of S. Then the semigroup algebra of S over K is semi-simple. Proof. Let us recall that a finite-dimensional algebra A over an algebraically closed field is semi-simple if and only if the dimension of A equals the sum of the squares of the dimensions of simple A modules. Therefore, to prove our corollary, we need to prove that for any I between 1 and k, the cardinality of the J cell Ji equals the sum of the squares of the dimensions of all simple modules whose apex is Ji. Okay, so let M be the number of left or right cells inside this Ji. Then the cardinality of Ji equals m squared times the cardinality of the H cell, and that's the cardinality of Gi. Let x1 and so on xri be a complete list of simple Gi modules. And let's choose them so that our simple module Vs with apex Gi is equal to Fi applied to Xs. Due our assumption on characteristic, the group algebra of Gi is semi-simple because the characteristic doesn't divide its order, and hence the cardinality of Gi equals the sum of the squares of the dimensions of simple Gi modules. Now we can compute that the cardinality of our two-sided cell Ji is equal to the cardinality of Gi times m squared. That's the sum of the squares of the dimensions of all simple Gi modules times m squared. But since we know that the dimension of the simple S module with apex Gi equals the dimension of simple Gi module times the number m of right classes, we can rewrite this formula as the sum of the squares of the dimensions of simple S modules with apex Ji. And this completes the proof. There is also an alternative approach to prove this theorem and even a more general result. So theorem, let S be a finite inverse monoid and K any field. Let Ji, Ei, and Gi for I between 1 and k be as described in the setup above. And let Mi be the number of left classes inside the two-sided class Gi. Then the algebra K of S, the semigroup algebra over K, is isomorphic to the direct sum of matrix algebras. So we take a direct sum, I between 1 and k, and then we have the matrix algebra of the size Mi times Mi over the group algebra of the maximal subgroup Gi. I refer to the following paper by Ben Steinberg, Möbius functions and semigroup representations theory, where you can find a complete proof of this theorem. On the next slide, we just simply discuss the general idea of the proof. And the idea is that we have the natural order both on the whole inverse semigroup S and in particular on the set of all idempotents of S. And since we have this natural order, we can use the Möbius function and the Möbius inversion formula for the incidence algebra of the corresponding poset and change the basis of the semigroup algebra in such a way that an element A of our semigroup in the new basis gets replaced by a linear combination, A overlined, which starts with A and then adds to it a certain linear combination of strictly J smaller elements with some integral coefficients, and so that the multiplication in the new basis becomes very funny. If we multiply A overlined with B overlined, we get AB overlined if and only if A, B, and AB all belong to the same J class. Otherwise, we get 0. And using this base change, we split the k of gi component in our semigroup algebra as a direct summand. And then it's very easy to see, because of how j classes of inverse semigroups look like, that that component is exactly isomorphic to the matrix algebra of size mi times mi over the group algebra of the maximal subgroup of that j class. Let's discuss one example in details. Let's look at the symmetric inverse semigroup ISN. So we consider this symmetric inverse monoid on the set 1, 2, and so on n. This monoid has n plus 1 j classes, j0, j1, j2, and so on jn, where ji consists of all elements of rank I. For a subset x of n underline, we have the idempotent epsilon x, which corresponds to x, which is the identity on x. So x is the domain, and this idempotent acts as the identity on this domain. The H class of epsilon x is naturally identified with the symmetric group Sx. The left class of epsilon x consists of all elements in ISN which have domain x. For an index I between 0 and n, let's denote by EI the idempotent epsilon I underlined, and in particular 0 underlined is the empty set. Then the maximal subgroup GI is just equal to the symmetric group SI. To proceed, let us briefly recall classification of simple modules over the symmetric groups. Let m be a positive integer, and Sm the symmetric group of all permutations of m underlined. Let us assume that K is an algebraically closed field whose characteristic doesn't divide m factorial. Then simple modules over Sm, over this field K, are indexed bijectively by partitions lambda of m. The simple module which corresponds to partition lambda is called the Specht module and is denoted by S upper lambda. The module S upper lambda has a basis, elements of which are indexed by the set of standard Young tableaus of shape lambda and content m underlined. This is usually denoted SYT sub lambda. For a standard Young tableau of shape lambda, call it T, the corresponding basis element is called a polytabloid and is denoted by E sub T. That's a specific linear combination element in a very explicit permutation module, which is constructed in order to construct the Specht module S lambda. And the set of all such polytabloids constitute the classical basis of S lambda, and one can write fairly explicit formulas how the elements of the symmetric group, or to the very least the elementary transpositions, act on these basis elements. Now let X be some subset of n underlined of cardinality m. Let phi of X be the unique order-preserving bijection from m underlined to X. Let us create the set SYT sub lambda upper X of all standard Young tableaus of shape lambda and content X. And these are obtained by taking the usual standard Young tableaus of shape lambda and applying phi X to their entries. Similarly, for each polytabloid E sub t, we can create a similar polytabloid phi x applied to E sub t, where we just substitute the entries of the original polytabloid using our function phi of x. And let us denote by L sub lambda the linear span of all these polytabloids phi x of E of t, where t runs over all standard Young tableaus of shape lambda, and x runs over all subset of n underlined of cardinality m. Then the space L sub lambda is exactly the underlying space of the simple ISN module that corresponds to the simple SM module S upper lambda, to the Specht module S upper lambda. The apex of this simple module L lambda is the J class of ISN consisting of all elements of rank m, so this is exactly this m. So let us now describe the action of ISN on this L sub lambda. Take an element sigma in the symmetric inverse semigroup and let us act by sigma on some basis element phi x of ET. If the cardinality of sigma of x is strictly smaller than m, which is the cardinality of x, then the outcome is 0. If the cardinality of sigma of x is equal to m, then we can restrict sigma to x, and we can write this restriction uniquely as the composition of some permutation tau in Sx, followed by the unique order-preserving bijection xi from x to sigma of x. Let us define tau prime, and that's an element in the symmetric group Sm underlined, such that phi of x after tau prime is equal to tau after phi of x. And note that xi after phi of x is equal to phi of sigma of x. So now we can describe what we will get if we act by sigma on phi x applied to ET, in the situation when sigma of x has m elements. We will get phi sub sigma of x of tau prime applied to ET. So tau prime is now an element of Sm, and ET is an element of the Specht module over Sm, so tau prime can be applied to it. We get a new element of the Specht module, and now we apply our bijection phi sub sigma of x to this new element. And it's very enlightening to compare all this with the usual construction of induced representations of groups. In fact, the two constructions are very similar, as both are defined using the tensor product, it's a tensor induction, with a bimodule that is free over the starting group algebra. So for group induction, the basis of the free module is given by choosing some representatives in cosets of our group modulo the subgroup. In our case of the symmetric inverse semigroup, the basis of the free module is given by the subset X of an underlined with cardinality m, because these subset index different H classes inside our left class, whose linearization is our bimodule. And each of these H classes is free over the original group of rank 1. Let's look at the special case. Consider lambda to be the partition M of M, one part M. Then the module S upper M is a trivial one-dimensional Sm module. So we have the unique standard Young tableau T of shape M, and so the basis of L upper M consists of all phi x of this ET, where x is a subset of an underlined of cardinality M. So given sigma in Sn, sigma applied to such basis element outputs 0 if sigma of x has less than m elements. Otherwise, it outputs a similar element phi sigma of x e of t if sigma of x has exactly m elements. In fact, in this particular case, our module L upper M is the linearization of the partial ISN act on the set of all subsets of n underlined of cardinality M. So here, a subset X of cardinality M is in the domain of sigma if and only if sigma of X has exactly m elements, so it's a similar subset, in which case sigma sends X to sigma of X. If sigma of X has less than m elements, then sigma of X is not defined. X is not in the domain of sigma. Another special case is the case of the partition 1, 1, 1, 1, 1, m parts of M. This is usually denoted 1 to the power m. The module S upper 1 to the power m is the sign module over Sm, and we have the unique standard Young tableau R of shape 1 upper m. Therefore, the basis of L upper m consists of all phi x of this ER, where x is a subset of n of cardinality m. Again, the elements of our module are in bijection with subsets of n underlined of cardinality m. Given sigma in Sn, sigma kills the basis element if sigma of x is too small, and otherwise, if sigma of x again has m elements, sigma applied to the base element gives plus minus the basis element for sigma of x, and plus or minus depends on the parity of tau prime. If we look at the formulas how defined, there is an element tau prime which comes from the sigma. If that is even, we have plus. If that is odd, we have minus. As a most special case, we can look at the case m is equal to 1. In this case, we have only one partition of 1. So it's both previous special cases at the same time. So in this case, the module L upper 1 is described explicitly on both of the previous slides. In particular, it has a basis which is naturally indexed by one element subsets of n underlined, that is exactly by the elements of n underlined, and the action of ISN is just the usual action of ISN on n underlined. That's a partial action. Therefore, L upper 1 is exactly the natural ISN module. That's a simple module over ISN. Some additional problems and questions at the end. Problem question 1. Check with all details that the semigroup algebra of IS2 over a field of characteristic 2 is not semi-simple. Problem question 2. Fill in all the details of the proof that uses Möbius inversion, that alternative approach to semi-simplicity. Problem question 3. Describe in detail the simple ISN module L upper lambda, where lambda is a partition of n. Problem question 4. Which of the simple ISN modules L upper lambda is the trivial module? So one module over any semigroup which is simple is a one-dimensional trivial module. For which lambda do we get L upper lambda isomorphic to the trivial module? And problem question 5. Check with all details that L upper m is the linearization of a partial ISN act. Thank you very much, and see you next time.